So I think we'll get started. Thank you all for coming. As you can see, I'm going to be talking about the Riemann hypothesis, and this is my second time trying this. So I'm going to try and match how long it took me last time, which was 25 minutes. Then we should be finished in time for next lesson. Okay. So the first thing I guess really to introduce is who Riemann was. I've got this. Riemann was a German mathematician in the, well, he was born in 1827, I think. There's a really nice book called Poetry of the Universe by Robert Osserman? R. Osserman, anyway, which I really recommend. But in that book, he makes comparisons between composers and mathematicians, contemporary mathematicians at the time. And so, for example, Bach is linked to Euler, both incredibly prolific and produced loads and loads of works, but also kind of across a range of different areas. And then compares Beethoven to Gauss, and then finally Riemann to Brahms, both German citizens sort of in the 1830s and onwards. And the similarity between these two is that they had a like really perfectionist approach to their careers. So, for example, Brahms spent 20 years, wrote 20 quartets, and published one of them in that time, and along with a few symphonies. And Riemann, almost even more so. He produced only like a handful of works and lectures, but each one was sort of really honed and fundamental to the area that it was in. So, for example, he created really the maths that's required for Einstein's general relativity, the idea of curved space in 4 dimensions. In a lecture shortly after his PhD, he introduced these ideas, and Einstein credits Riemann with his work. So the Riemann hypothesis, though, is in the area of prime numbers, but also in the area of complex sort of analysis and complex functions. So we'll start with what hopefully we all know, the prime numbers. So 2, 3, 5, 7, and so on. We're familiar with them. They're quite easy to define because they're integers that have only got themselves and 1 as factors. But they're very hard to produce or to find a pattern. So by comparison, the square numbers, we've got 1 squared is 1, 2 squared is 4, 3 squared is 9, is where I get anxious I'm going to make a mistake. But there's a really clear pattern, and if I wanted to calculate the 300th square number, it would be quite easy to do. Just take 300, square it, and that tells me my 300th square number. But the primes is much harder to do. So if I ask the question, what's the 300th prime number? I don't think we would know how to do that, and we'd probably find ourselves counting up the primes as we find them one by one, which is really the best thing we can do. So really, what Riemann was interested in was producing a function that gives you the primes. And he looked at it slightly differently. He defined pi of x as the number of primes less than or equal to x. So for example, pi of 3, how many primes are there less than or equal to 3? What's the answer? Come on, shout it out, you know. Less than or equal to 3, how many primes? 2. Fantastic. Similarly, pi of 4 is also 2, so 2 primes less than or equal to 4. And so you get this step function which jumps up by 1 each time there is a prime number, and it counts the number of primes less than any given number. So this really is what Riemann wanted to understand. And there was a start to this from Gauss, who was Riemann's supervisor at Göttingen University. Gauss, when in his teens, this was before computers and calculators, they had tables published of prime numbers, one thing, and logarithms, another thing. Some of us won't have met logarithms yet, but they had tables of logarithms. And he spent his early teens and mid-teens looking through these tables and recalculating them, he found a number of mistakes in the published tables, and also noticed a link between logarithms and the number of prime numbers less than a given number. And so then Riemann improves slightly on it. I'm not going to go into that, but it gives you this approximation to the pi function, the number of primes less than x. You can see it's a curved function, not a step function, but it does give you the distribution of primes quite accurately, and this was a really sort of important step in understanding the pattern of primes. It's a bit complicated to say what this function is, but it's to do with logarithms, and you can look it up. But we can see that because it's not a step function, it's a smooth function, sometimes it over-guesses, sometimes it under-guesses the number of primes less than that given value of x. And so if you look at the error of this approximation to the actual correct number of primes, sometimes it's too big, sometimes it's too small, then it's too big, then it's too small. And if you plot it on a particular scale, you get this. What does this kind of shape make you think of? Any thoughts?
Random noise.
Random noise, but noise perhaps. Yeah, sound waves, or if you've looked at recordings and sort of looked at an oscilloscope, then you get this kind of pattern for noise. And so this is how Riemann approaches this. What he wants to do is, can I actually write down what this function is? Because if I can write down what this function is, it looks chaotic and random. But if I can write it down, then I can add it to my approximation, and I'll get the exact prime number function. And so that's what he does. He manages to do that. So let's think a bit about the maths of music, the physics of music. We may or may not know, hopefully, I expect we've seen this in physics, that if you've got a sound wave, an air wave, pressure wave like this, then you can break it down, thanks to the work of a mathematician called Fourier, a French mathematician, can break it down into component parts that are perfect sine waves. So this sound wave can be broken down into an A, a C sharp, and an E, and they might have different volumes, they've got different frequencies, but when they're heard together, they create this more complicated function. Is that familiar? Fantastic. So what Riemann does is he finds these fundamental frequencies, harmonics, of the noise of his approximation, his error function. And how does he do that? So this is where we bring in the Riemann zeta function. So it looks kind of complicated. Some of us will be more familiar with others in terms of this notation. But the basic idea is you plug in a number, this is how a function works, you plug in a number and you get out a number. So in particular, one way that you can define it is in terms of this infinite sum. So if I wanted to do zeta of 1, I just replace s with 1 everywhere. I get 1 plus 1 over 2, plus 1 over 3, plus 1 over 4, plus dot dot dot. Does anybody know that series? I know you guys do. This is called a harmonic series, yeah, really well done. And it diverges, which means that this actually doesn't equal anything, this equals infinity. So the zeta function doesn't give you a nice output for 1, but it does give you outputs for other numbers. Like if I plug in 2, I get 1 plus 1 over 2 squared. If I replace s with 2, I get 2 squared, 3 squared, 4 squared, 5 squared. So 1 over 4, 1 over 9, 1 over 16, dot dot dot. And this turns out to be equal to pi squared over 6, which we don't have time for today, but it gives you a valid output. So that's quite fun. So that's how this function works, but it gets more complicated because the functions that I've been talking about, you plug in a number, you get out a number. Those of you in year 13, or maybe lower down, will be aware of complex numbers. So really what's happening is you're plugging in a complex number and getting out a complex number. But for those of us who don't know what complex numbers are, one way of thinking about it is instead of putting in a number, which is a one-dimensional, it's from the number line, one-dimensional thing, and getting out a number, which is from the number line. Instead, you put in a point on the plane and get out a different point on the plane. So it's taking a two-dimensional number to a two-dimensional number. So if we think about a sort of a usual function, so f of x is x squared, I've talked about the square numbers quite a bit. If we're thinking about putting in a number and getting out a number, one way we can represent that is to have our input number line being represented horizontally and our output number line being represented vertically. And then we just, for each input, we plot the corresponding output, and that gives us a graph of the function. We'll be familiar with graphs of the function. So this is one-dimensional input, one-dimensional output gives us a two-dimensional graph. So if we wanted to represent the Riemann zeta function using a graph, we've got a two-dimensional input, a two-dimensional output, so it needs to be a four-dimensional graph. And so then you get lots of different creative ways of representing that, which you'll have seen one of them on my poster. But it's hard to do that, obviously. Because of Riemann's background in sort of higher dimensional curved spaces, he could have a stab at this, but there are a few ways to think about it. One way is to think of it as a transformation. So you start with all of the points in the plane, two-dimensional plane. You apply the zeta function, find out the output points, and that just moves points to a different place. So you've got input points, and then when you apply the function, you get output points. And so you can see it as a kind of movement of points on the plane. So this was just 4 points, but if we look at the whole plane, you can get a sense of what the function looks like by kind of rolling forwards the function and going from a grid of input values to this shape of output values. So the Riemann zeta function is really pretty. There are lots of different ways that make it look pretty. This is one of the ways. You get these lovely symmetrical kind of arcs and circles. You can see that there's a symmetry down between 0 and 1 of some description. You can also perhaps see, I said that when you try and plug in 1, it goes wrong, you get infinity. You might be able to see, if you focus on this point 1 there, that's plugging in 1, you're going to see it be kind of torn apart by the transformation. It gets ripped out from 1, and that's representing the fact that you can't plug it into the function. Okay, another way is the poster that you've seen, and for this one, what you're looking at is the input plane, 2 dimensions, and for the output, we need 2 dimensions. We represent it by how dark the colour is as one of the dimensions, and what colour, what hue it is for the other dimension. So over here, you've got all of your outputs are real numbers, which is why they're red, but then these pretty colours are where you're getting complex number outputs. And the darker it is, the closer your output is to 0, to the origin. So over here you're getting really big outputs, and then over here you're getting really small outputs. And that again is a really pretty image. And there it's again quite a symmetrical picture, but also an incredibly complicated one to understand in great detail. So what's the point of this? So remember we were looking for those fundamental kind of frequencies of the error function to try and get the individual notes that make up that sort of noise, that random noise. So what he's interested in is the zeros of the zeta function. These are the input points that get moved to the origin by the transformation. So any points that once you apply this transformation, they end up at 0, 0 in the center of your graph. So there are a few places where this happens. It happens at -2, -4, -6, -8, -10. These are called trivial zeros. They're not interesting. They're sort of built into the function in a way. They're like they're an artifact of the process used to make the function. but then it can be shown that any other zeros, and there are infinitely many of them, lie in this shaded strip here called the critical strip between 0 and 1. And Riemann went, so it was a 9-page paper published in 1859. He calculated by hand some of these other zeros. I think he calculated maybe 5 or so, and there are infinitely many. And he found that all of them lay actually right in the middle of this region, lay on that vertical line between 0 and 1. And he hypothesized that that will always be true. He said, I think it's very likely that all of the zeros are going to lie on this critical line. And it's now being checked for this many zeros, which is something like 10,000 billion, depending whether you're going with the old British billion, 10 billion, or the new billion, 10,000 billion. Anyway, they checked it by computers that first this many zeros do in fact lie on that line. So his hunch based on 5 looks likely to be true. But nobody has been able to prove that they all do. And this is the Riemann hypothesis. So a successful proof that all of the zeros, the non-trivial zeros, lie on that center line would be worth $1 million. And it's been open for 150 years and not been solved. So how does this feed into the original idea? Well, if you look at what Riemann realized, and I have no idea how he did this, if you look at those zeros, infinitely many zeros up the critical line, they've got, well, they've got a sort of horizontal position, which we're hypothesizing is all the same, and a vertical position. And the horizontal position gives you how loud the note is, and the vertical position gives you the frequency of the note, and each zero gives you a note in the error function of the prime counting function that he produced. So really one sort of way of thinking about the Riemann hypothesis is that there's no dominant note kind of in the pattern of the primes. They are pretty much as random as possible. There's not one louder kind of oscillation that influences the primes more than any other. They're all sort of equal in their influence on the location of the primes. So that's how he gets the prime function, and you can have a look at, this is going to take us to the first 200 zeros being applied to his original approximation compared to the actual prime number function. You can see the more zeros you include, you've got these oscillations, but they're getting closer and closer to actually approximating the correct prime number function. So what he proved, and he did prove this bit of it, is that if you take all infinitely many zeros and do this process, you get the exact step function that counts the primes. So there is a function that produces the primes, there is a pattern underneath, it's incredibly complicated, it involves complex numbers and an unproved hypothesis, but there is this pattern sort of behind them, and it's not practical really, because you can't calculate infinitely many zeros and then do an infinite sum necessarily to count the number of primes, but it is very beautiful that he was able to do this. So then finally, I wanted to talk about a few sort of things that have happened recently in the search to understand the Riemann hypothesis. So we had a senior society speaker actually come a couple of years ago called Dr. Nina Snaith from Bristol University, and I don't want to just reproduce what she said, and I'm basically lifting straight from her talk, but I thought it was really interesting. The way that this came about is mathematicians from different disciplines were gathered together at a conference, and one had been working on the zeros of the Riemann zeta function, in particular looking at how they were spaced vertically rather than their position horizontally, and looking at the statistical spacing, kind of what they looked like on average going up the critical strip. And another was a mathematical physicist in the area of looking at atomic energy levels. And they were just chatting over lunch, and I think the physicist saw the work that the mathematician had been doing and said that distribution of zeros looks really similar to the energy levels of uranium or a heavy element. So what do they mean by that? Well, you've got different types of distributions of things. So here we've got periodic, which is a regular distribution of lines vertically upwards. Then you've got proper sort of true randomness. And in true randomness you actually get big spaces of gaps and groups of clustered things. It's one way to spot somebody's faked random data is they tend to spread things out more, thinking that in order for it to be random it needs to be spread out kind of. But actually they do cluster and they have these big gaps. Then you've got the energy levels of erbium, which is the sort of different amounts of energy that electrons can have in the erbium atom. And then you've got the zeta zeros. This is kind of where they would be looking up the critical strip. And then you've got the positions of the primes. And whereas the primes do look like a random distribution, with big gaps in places and similarly kind of compact groups, the zeta zeros actually seem to be behaving a lot more like the energy levels of an atomic nucleus. So there seems to be a kind of process that's pushing the zeros apart from one another, like in energy levels in an atom. So how does this help us? Well, what's been recently done in 2017 or so is they've been able to construct a sort of an energy system that produces precisely the zeta zeros as the energies of that atom. And if they could show a certain property of that system, that would correspond exactly to proving the Riemann hypothesis that all of the zeta zeros are on the x equals a half on the symmetry line down the middle of the critical strip. Unfortunately, the easy way of doing that turns out not to be true. So real physical systems have a particular property that just would mean that this would be automatically true, and unfortunately the constructed one doesn't have that property, so it's not there yet, but it does seem to be perhaps an avenue where mathematical physics might be able to come up with a result. And then finally, I just wanted to end by talking a little bit about the end of Riemann's life. So Riemann, he fled Göttingen during the Austro-Prussian War, took a few trips to Italy, and unfortunately died of tuberculosis at the age of 39. And because of his perfectionist nature, he didn't like unfinished work to be published. So there was a whole load of work that was destroyed. There was one notebook that survived with this is his writing. And some of the advances made in the 20th century actually eventually came from people finding his notebook and making sense of it, which was incredibly hard to do. So they are credited with it because understanding his notebook was a feat of sort of mathematical genius and understanding. But actually it came from his work, and who knows how much of it could have been lost when his unpublished works were destroyed due to his over-perfectionism, so it's a moral lesson. And yeah, I think that might be the end of the talk. Thank you. Any questions? Any thoughts on how to prove it? Oh yeah, Emma.
Sorry, I might be really silly, but how is the zeta function linked to the prime number step function? How is that linked?
So it's linked by finding the zeros of the zeta function. So those are the points that are mapped by the zeta function to the origin. If you take those zeros, use them to create notes, here's all getting very unrigorous and unmathematical. Thank you for coming, guys. Yeah, if you use their horizontal position to be their amplitude and their height to be their frequency, roughly speaking. Actually, there are some other things going on. Then you add all of those together, then you get this function, which when added to the Riemann approximation gives you the exact step function. And you can see that's what this this animation was showing us. This was after only adding a few zeros, then adding increasingly many of those oscillations. It gets closer and closer. So it's via quite a complicated sort of loop, but yeah, good question. And there was another question. Yeah?
Where does the Million Problems come from?
It comes from the Clay Institute, and I couldn't say what that actually is. Do you know what the Clay Institute is? There are 10, I think, or it's gone down since, because some people have proven them, but 10 unsolved maths problems that are worth $1 million. 7. Did it start as 7? Yeah, and now there are 6, because they did the Poincaré conjecture, and the guy who solved it was a Russian hermit and refused the money. So that's fun. Yeah, so that's where it comes from. I actually had a dream during one of the other Millennium problems is called the Navier-Stokes problem, and it's about fluid dynamics. And when I was at university, I did a lot of fluids courses. That kind of actually what ended up being my specialty. But also, I really love this stuff with Riemann surfaces and Riemann complex analysis. So I was doing those two subjects mostly. And in exam term, when I was just spending all of my time reading these notes and doing these problems, I had a dream that I showed that I didn't solve either of them, but I showed that they were the same problem somehow. So I showed that if you started with this 4-dimensional Riemann surface, and then you imagined that it was a fluid and allowed it to flow, then somehow that would prove that they were the same problem. And I told my lecturers, and they laughed at me. So who knows? That might be an avenue to go down. Maybe I have those genius dreams, like the helix or whatever. But I doubt it. Okay. Any other questions? No. Thank you very much. Oh, quickly.
Do you think it is solvable?
I think it's true. Which is not quite the same as saying that it's solvable, but it does mean that it's not disprovable, because to disprove it, all you need to do is find one example that is off the line. Once you've tested 100,000 million, it seems very likely to be true. And I personally, my philosophy of maths is, my other Nicholson lecture that I gave is 2 years ago, or 3 years ago, was about incompleteness of maths and how there are unprovable true statements. So it's possible that this is an unprovable true statement, but I don't believe it is. I believe that there is a way of understanding the function, maybe at a different level, that would prove the Riemann hypothesis.
It's really good for talk.
That's what we just had to say.
Yeah, well, it's on the NLCS Maths website, Gödel's incompleteness theorem. Great, there you go. Close 2 lectures. Thank you.
Thank you very much.